Hello, so here we have the star of my videos, Sir Shackleton the Explorer, and he's purring away, and I don't think he realizes that his other two, you know, um, not siblings, but his other two co-cats, Mop and Sally, had cameo appearances in the previous videos, so didn't want him to know because don't want him to be jealous. So I'm continuing my discussion where I left off on the previous video about the climate sensitivity. So by way of summary, there's three types of sensitivity, and I'll be talking about the equilibrium climate sensitivity. Okay, which is you double CO2, what does the temperature of the planet go up to? And the transient climate response is what it goes up to. If you increase CO2 1% a year, and when you reach the double value, what's the temperature? That's the transient climate response for a doubling of CO2. And then if you leave more time, the heat gets dispersed through the deep ocean and comes out and so on. So that's a longer term temperature that's reached in equilibrium climate sensitivity. And there's an even longer one, Earth system sensitivity, which accounts for the changes in ice sheets, etc. So the accepted value is 1.5 to 4.5 C for the equilibrium climate sensitivity, and that hasn't changed much. There's a paper in 1979 called the Charney Report, and it came up with that number, okay, that assessment number. But a lot of the uncertainties have been eliminated, and we basically essentially converge to that number even now. So this is a study. This is between 2001 roughly and almost present day, and this is the equilibrium climate sensitivity, the ECS, in all of these different studies. So you can see the 3 to like 1.7 to 4.2 in the IPCC third annual report, 1.4 to 7.7, and so on. There's all of these different ranges. So some of the highest ones, they go up to 9 Celsius. Like this guy here, the climate sensitivity varied from 0.82 to 10 actually. This is a 2016 study. So the numbers vary quite a bit, but we've kind of converged on the 1.5 to 4.5. Most of the numbers fall in that range, right? 1.5 to 4.5 or so. Main change being 3 for ECS. And there's models. There's constrained models. Instrumental is the brown, paleo purple. Combined approaches is the the shading there. Okay, so somewhere in that ballpark. One of the problems is that this actually changes depending on the initial state. So in other words, if you double from 280 to 560 parts per million, you'll get a certain number. But if you start at a warmer climate, say 400, and double to 800, you'll get a much larger value for ECS. That's what the most recent paper shows. So, these are the different types of studies again. So the typical, the equilibrium, the averages, if you like. So the models here, 2.1 Celsius to 4.6. Constrained models, slightly higher. Instrumental, paleo, going from 2 to 5.2. All studies, 1.8 to 4.6. So basically 1.5 to 4.5 with 3 in the middle. That's the most accepted number. And I think there's another figure. This is a transient climate response. So it's lower, 0.9 to 2, 1.2 to 2.4, 0.8 to 2.1. These are blended CMIP5 models. So this is what happens on the short term without the exchange of heat with the oceans. Okay, so there's all of those numbers. This is an excellent paper, so be sure to have a look at it. Okay, so basically we've defined enough things that we can go right to the paper, and you can access this. Okay, so what this shows is basically so they looked at the Eocene greenhouse, and modeling studies suggest in order to achieve the global warmth that they saw, that the Earth saw in the early Eocene, warmer climates must be more sensitive to CO2 forming than colder climates. Okay, so they used a new high-resolution boron isotope-based CO2 record. Okay, so from the boron they could get the pH of the ocean, and from the pH they could get the amount of CO2. Okay, and they also had global mean temperature numbers, and they found that the equilibrium climate sensitivity was higher during the warmest intervals of the Eocene. Okay, and the range of the ECS, 1.5 to 4.5 degrees Celsius per doubling, is unlikely to be appropriate for high CO2 warm climates of the past. So therefore, this is very important to the equilibrium climate sensitivity today and how much we can expect the Earth to warm, as CO2 continues to increase. Okay, so it's a very good paper. You can access it, but I'm going to focus on some of the figures. So these are some of the ocean drilling sites, and they're put onto a map of the Eocene. So this is the location of the drilling sites when you account for continental drift going back in time. So they're measuring conditions back when the Earth looked like this, was in this configuration. The continents were in different places. India hadn't even slammed into Asia yet. Okay, so this is the position of the continents back in the Eocene when the data was collected. And here's some of the data. Like I said, I'm just focusing on the figures. So this is 35 to 55 million years ago. 56 is the Paleocene-Eocene Thermal Maximum. Okay, so this is the oxygen del 18O oxygen isotopes, and you can relate this to temperature. So up here, as you go up here, it's higher temperature. So the temperature spiked in the Paleocene-Eocene Thermal Maximum. This is the Eocene Thermal Maximum 2 here, this area here, right down here, very hot period as well. Early Eocene climate optimum here in this region, warmer temperatures overall. Mid-Eocene climate optimum here in this region, and Eocene-Oligocene transition. This is when we went out of the Eocene into the Oligocene, temperature dropped, CO2 level dropped. Okay, this is the CO2 concentrations in these different times. So spiking here is corresponding to the very high temperatures, and the CO2 was produced from lots of volcanic activity, we think. And CO2 levels generally high here. This is 2,000 ppm, 1,000. We're way down at 400, right? We're off the chart down here right now. So CO2 levels were much higher, and you can see how they dropped as we, this is older, this is younger. As we come back to the present, they started dropping, but they were still, for this long period of time, they were over 1,000 parts per million. And this is the surface pH of the ocean. So, the pH, this is higher pH, more basic. This is lower pH, more acidic. So, we reached, not quite, but close to 7.4 pH on the surface here. And then down to, an increase. So more acidic here when there's more CO2, less acidic here when there's less CO2. Okay, so this is the CO2 again. This is same sort of time scale here. And this is the del 18O, which is the temperature, so temperature spiking. So I showed you this plot, and I showed you this plot, and there's other isotopic elements that give you more information about what was happening back in this time period. So these temperatures are also captured with the del 13, the carbon isotope numbers. And here again is the CO2 in parts per million. And this is the sea surface temperatures at those time periods. So look at the sea surface temperature This is 30 degrees Celsius, 35, 40, 45 degrees Celsius in the Paleocene-Eocene Thermal Maximum. Huge temperature, you know, really extremely warm temperatures. Stuff couldn't live near the tropics. The plankton must have been massive, massive hurricanes back in that time period. Okay, and you know, here's the sea surface temperatures dropping as we get closer to the present time, but there's still well over 30 for a lot of the duration. Okay, and then we can, this is again the, this is the climate sensitivity now per doubling of CO2. Okay, so right now, you know, the common number for equilibrium climate sensitivity is 1.5 Celsius to about 4.5 Celsius, which is this band here. Okay, this brown band here. And you can see how in order to get these temperatures back in the Paleocene-Eocene Thermal Maximum, you would require a climate sensitivity more like 14 degrees Celsius. So per doubling of CO2 back in this time period, you know, so say from 1,000 to 2,000 ppm, you'd have 14 degrees, you know, 14 degrees Celsius increase per doubling. Okay, way, way higher than the range we think now. And then as you go through the Eocene Thermal Maximum 2, that number dropped down here to something like, well, I guess it's something like 6 to 10 or so, and then drop back, so, and then drop down into the ranges that we see here. So from about here, you know, 42 million years ago to 33, the climate sensitivity was in these regions. So it looks like, you know, the lower the temperature that you start at, the lower the sensitivity. So this is what you know, as you get warmer and warmer and warmer environments, then the sensitivity goes way up and the warming is greatly accelerated even more. This is global mean temperature for given CO2 levels, so 500, 1,000, 2,000 ppm. And this is absolute temperature, so 500 ppm, you know, about 21, 22 degrees Celsius, global mean temperature expected, and up to 35 Celsius global mean temperatures when we, you know, at these sort of CO2 levels. And this would be, this is a, you know, global mean temperature back in the, you know, in the Eocene, you know, reaching, you know, close to 40 Celsius in the Paleocene-Eocene Thermal Maximum, you know, over 30 to 35 for a good chunk of time, and then dropping, you know, as we got closer to the present. So this was certainly an amazing time, the Eocene, a very, very warm time. And remember that, so the key is, you know, again, how long did it take to reach this warming? It seemed to take probably from 1,000 to 5,000 years to reach the warming, right? To have the CO2 being released by the volcanic activity, and that greatly warmed the temperatures over that time period. Most of the species on the Earth managed to survive. There was 20% of plants, plant extinctions. I mean, stuff couldn't really live at the tropics. The poles reached the same temperature as the tropics, so we had lush tropical vegetation and plants and animals both in the Arctic and in the Antarctic. The Arctic stayed above freezing temperatures year-round, and with no temperature gradient between the poles and the equator. Of course, the jet stream would have basically collapsed, and we would have had it would have been monsoon type behavior affecting the storms, etc. So, you know, if we think of, we have torrential rains now, imagine what they would be like back then, and also mega droughts in other places more inland. So very, very tropical near coastlines, very, very dry inland, and, you know, a very, very different world, and a world that we're rapidly heading towards with present-day climate change. So thanks again for listening. Go to my website, paulbeckwith.net. Please consider donating to support these videos. Thanks again.